Hi there! Today we're going to learn about a popular and very simple coding problem, TwoSum. Trust me, this problem is much easier than it sounds. By the end of this video, you'll not only understand it, but you'll also feel confident solving it in multiple ways. Let's get started, and I promise you'll be like, oh, that was easy. So, what's the deal with this TwoSum problem? Imagine you're given a list of numbers and a target number. Your task is to find two numbers in this list that, when added together, give you the target number. Easy, right? Let's see a real-life example of this. Say you're shopping online and you have a gift card worth $100. You want to buy two items from a list where the prices are scattered. How do you quickly figure out which two items exactly match your gift card value? That's the TwoSum problem. You're finding two numbers from a list that add up to your target, in this case, $100. Alright, let's dive into the ways we can solve this. There are a few approaches, and each one has its own perks. Approach 1. Brute force, aka the try everything method. This first approach is super simple, almost like trial and error. The idea here is to check every pair of numbers in the list and see if they add up to the target. Here's a real-life example. Imagine you're at a yard sale with a bunch of price tags. You pick up two items at a time and see if they add up to your gift card. You keep doing this until you find the right pair. Here's how we do this in JavaScript. In line 1, we define a function, TwoSum, that takes in the list of numbers, nums, and the target. In line 3, the first loop picks a number from the list. In line 5, the second loop checks all the other numbers against the first one. In line 7, if the sum of two numbers matches the target, we return their indices. In line 14, if no valid pair is found, we return null. Now, what's the time complexity of this? It's O of n squared. This is because for each number, we're comparing it to all the other numbers. It's not very efficient, but it's simple. And what about the space complexity? It's O of 1, because we only store a couple of numbers, so we don't need extra space. Approach 2. Two-pass hash table, aka the smart map method. In this approach, we're going to be a bit smarter. Instead of checking every number with every other number, let's map each number's value to its index, and then just check if the complement, what we need to reach the target, exists in our map. Now, here's a real-life example of this. Let's go back to the yard sale. But this time, you keep a notebook where you write down each item's price and where it's located. Then, as you look at new items, you just check if the complement is already in your notebook. Much faster, right? Now, how do we do this in code? In line 3, we create a map to store each number and its index. In line 6, the first pass. We fill the map with numbers and their indices. In line 11, the second pass. For each number, we calculate the complement that would add up to the target. In line 14, if the complement exists in the map and is not the same number, we return both indices. Now, what's the time and space complexity of this? The time complexity is O of n. We go through the list twice, but in linear time. The space complexity is also O of n. We store all the numbers in a map, so it requires extra space. Approach 3. One-pass hash table, aka the super-fast method. This is the most efficient approach. Instead of doing two passes, one to fill the map and one to check for complements, we do both in one go. As we're adding numbers to the map, we also check for the complement at the same time. Now, here's a real-life example of this. Imagine you're walking through the yard sale, jotting down prices, while also checking your notebook in real time. You write down a price and immediately see if what you need is already written. Now, how will we do this in code? In line 3, we create a map to store numbers and their indices. In line 7, as we loop through the list, we calculate the complement. In line 9, if the complement is in the map, we return its index and the current number's index. In line 14, if not, we add the current number to the map. Now, what's the time and space complexity of this? The time complexity is O of n, because we only go through the list once. The space complexity is also O of n, because we're still using a map to store the numbers. And there you have it. We went over 3 different ways to solve the TwoSum problem, from the straightforward brute force approach to the efficient one-pass hash table method. In real life, this problem shows up more than you think. Whether you're trying to optimize the way you shop or build efficient software for managing datasets, knowing how to quickly find pairs of items that add up to a specific number is super helpful in computer science, especially in areas like database management, financial systems, and even game development. I hope this was clear and easy to follow. If you like this video, don't forget to subscribe and let me know in the comments if you have any other questions. Happy coding!